Hey guys, your boy Chile here. Welcome back to Hardware 3D. Today's topic is a dynamic constant buffer. Now before we get started, look down at the bottom of the video. You're going to see a number down there. I don't know what the number is, but it's going to be pretty big. That's the number that represents the length of this video. It's going to be a long boy. I just started recording. I don't know how long it's going to be, but I'm sure it is going to be long. Maybe it's going to be like an hour long or so. And I know not all of you guys are going to be interested in the software engineering side of things. You're more just interested in, show me the direct 3D, show me the algorithms, or show me the API. So what I've done with this video is I've structured it. I've put all the essential information right at the beginning of the video. So for those of you who aren't interested in, software engineering or C++ metaprogramming, just watch the first part. The very first part, all I'm going to show you is the basic interface, how to use the system that we build in this video. And if you know this, you won't get lost in future videos that are about things you are interested in, like, for example, real-time shadows, character animation, all right? So for those of you who aren't interested in the whole deal, you can just stick around to the very first part and you'll get an idea of how the system works and you won't get lost in future videos. For those of you who are more interested in that software engineering stuff, stick around for part 2. I'm going to talk about the motivation, the reason why I create the system, the problems that it solves, its advantages, and I'm going to talk about just the general overall design of the system, how it's put together, all the components. Then if you're really interested in all the details, stick around for part 3 and I'm going to walk through the code. I'm not going to tediously explain every single line of code, but I'm going to hit all the main points and I'm going to focus on some interesting techniques that I use. All right, let's jump into it. Here is the repo. Here, this commit is the beginning of the changes for the dynamic constant buffer. And here is the end. And we're going to be spending most of our time just looking at the finished product. Now, if we check out the code at that commit, there's one important file that I've added called testing.cpp. So as I was building this system, as I was adding features, I wrote tests for them to validate that they actually do what they're supposed to do. And instead of just writing some throwaway code and then deleting it afterwards, I decided to keep it in this file here. It can be reused. If I ever make changes, I can validate that all the old tests still worked. That's the basics of automated testing, right? So in this file, let me just show you a very simple example of how to use dynamic constant buffer. So you include dynamic constant.h. All the stuff lives in the namespace DCB for dynamic constant buffer. First thing you got to do, it's a data structure. It has a layout. So you have to describe the layout before you create a buffer of that type. So we do that at runtime. First, we create a raw layout. And we'll just call this one lay. That's just an empty structure now. We have to add some members to it. So let's go lay.add, and we want to add DCB, and there's a bunch of types you can add. Basically stuff that you would see in an HLSL constant buffer. So like float, float2, float3, float4, just your standard vector types. There's also matrix and bool. Let's add a float. Keep it simple, right? Start off with here, and we'll call it floaty. That sounds like a good name. All right, so now we've described the layout of our data structure. Let's actually make that bad boy. We'll go auto buff is equal to DCB buffer, and we got to give it the layout. So we can instead move that in. Don't waste any resources. Don't make any unnecessary copies. So we'll move our layout into here. That creates the buffer. Now let's use the buffer. Let's access some data. Let's write into our buffer. So we go buff. Now we want to access the member floaty. You just got to pass that string in there. Floaty, that's the key. And there's a lot of metaprogramming mechanisms that go on under the hood that allow us just to assign a floating value right in there with a simple assignment. And it just works. I mean, it looks like code that you might see in a more dynamic language like Python or JavaScript, but it's C++. It's almost as if we've extended the language itself here. That's the whole idea of metaprogramming, right? And it's going to be very intuitive, very easy to read design. And I feel like it's going to actually make the future tutorials easier. So for those of you who even aren't interested in this metaprogramming stuff, you're still going to gain benefits because it's going to make the future videos on topics you are interested in easier to digest. But anyways, so we store a value into our dynamic constant buffer. Now let's verify that was properly stored. So we'll go float f is equal to buff at float. How many of you guys see the problem here? So you've probably caught on, but we created it with a member called floaty, but we're accessing it as float. Now, because this is dynamic at runtime, the compiler can't catch this. But we're still going to get diagnostics. When I try to access float, it's going to throw an assertion. It's going to say tried to resolve. You can click retry, and you can go up the call stack and you could figure out where shit went wrong. And we can see it went wrong right here. So it's still possible to catch those. I've put in lots of assertions and stuff like that. So it will catch your mistakes. It won't just silently fail and cause weirdness that's hard to debug. So let's give this the correct names now. We're step. We're going to store into floaty. It worked. And then we're going to load back out, and it should give us a 1. And it does give us a 1. We've round tripped our data, and its integrity is intact. Beautiful. And I'm sure you'll agree this syntax is pretty easy to understand. All right, let's spice things up a little bit. We're going to put 2 members, one float3 and one float2, and we're going to assign to them. So we set up the layout and we build our buffer. Now the way the buffer is set up, I'll talk about this more in part 2, but there are 2 main parts to it. There's the actual bytes, just a raw contiguous byte buffer of the actual values. And then there is a layout, and this is a tree structure that describes, it's the map of those bytes of this buffer, right? Because the buffer is a struct, can have multiple members. Some of those members can be structs with members inside of themselves, and you can also have arrays of structs. So it can get quite complicated. You need a map of that landscape in order to figure out where the bytes are for a given, key name or path. So we can expand this buffer of bytes. We can see that they're all set to 0 to begin with. Now, when I write to floaty, which is the first member here, you're going to see what you expect. You're going to see, 4 bytes per float, 3 floats. So you're going to see the first 12 bytes are being set to various values. Okay. Now, what happens when we try to write to floatuti? You're going to see these bytes are being set. And you might be saying, well, what's this hole here? Well, that's one of the beauties of this system. It automatically adds padding so that the layout of this buffer of bytes exactly matches the layout of an identical buffer on the HLSL side. So you don't have to worry about alignment and packing and all the rules for HLSL. That's all automatically taken care of for you. Once you have this buffer, you can just copy those bytes directly over to the GPU and they will be aligned properly for access from your shaders. Like I said, there's many checks that go into here that will aid you in creating code that doesn't have bugs. So stuff like adding a duplicate key into a data structure here, it's going to throw an exception, right? Adding duplicate name to struct. Similarly, if I try to write the wrong kind of data to this member here, you're going to get another exception, right? So it's dynamic, but it's also type safe, at least when you're running in debug. When you're running in release, a lot of those checks are removed to improve performance. Now, what's interesting is because it's dynamic in runtime, it can't perform that check. It can't tell whether float3 is the right type for this until it actually runs the code. However, if you tried to assign to it a value that just isn't in the system at all, like let's say I tried to assign to it a string. We got some metaprogramming in there. It'll tell you right now, unsupported systype used in assignment. And if you click here, it shows you exactly where the problem was. So there's even some support for compiler checking of your expressions, where it's possible. By the way, if you're interested in what kinds of types are supported in the dynamic constant buffer, you've got float, float2, 3, 4, matrix, and bool, and I'll probably add integer and maybe some other ones in the future. But you can go to dynamicconstant.h, look at the very top, and you'll see the list of supported data types. Now, as I've alluded to, you can have nested structures. So how do we do that? Well, it's the same idea. It's just another member of our base structure. So we're going to add DCB struct. Makes sense, right? And it's a member. It's got to give it a name. So we'll go structy. That's a good name, right? And now we got the structure, but we have to give it some members. You can't just have an empty structure. It doesn't make any sense. So how do you add members to a member? Well, you just key into our layout. So we'll do structy.add, and we'll just add a float here. And you might be saying, Chili, don't these names overlap? No, because they're in different structures, right? This structure is inside of this one. It's not the same level. There isn't any ambiguity. There isn't any overlap in this situation. And then again, to access that, it's pretty simple. key into the buffer to access the nested structure, and then you key into that structure to access the leaf member, the float. You can set that up. And then here we can load that value. All right, let's test it out. So we add a float to our nested structure, create the buffer. Let's set that. And if we load it, 420. Okay, round trip, no problem. Now the final type of member you can add, the second aggregate type, is an array. So you can add an array, and just like everything else, you give it a name. We'll call it R, matey. But you might be saying, well, we've added this array, but we don't know what type it is. We don't know how many elements. Yeah, so you actually need a two-step process to set up an array. First, you add. Then when you have the array in there, you have to set its type. And we'll just say the type is DCB float. And the number of elements, we'll give it 10 elements. And the access, again, is what you would expect when indexing into an array. Instead of using a string, you're going to use an integer. And F3 here, we can see, yeah, we round trip our data, no problem. All right, now let me show you the most complex scenario we have, which is adding an array of structures. So the first part is simple enough. You add the array, you set its type as a structure, so I have 69 of them in the array. But now, how do you actually define the structure, the shape of this structure that's in the array? Well, there's the tricky part. You go lay, this should be R2. We go R2 dot T, and that accesses the type of the array. And once we have the type, then we can add to it, because the type is a structure. We can add to that structure. So let's add a float 3, and we'll also add a single float in here. And here's what that access would look like. We run it, and we see, yeah, we get no problems. Expected result right here. So there you go. There's the most complicated scenario, and you can nest this however deep you want. It's completely free. It's completely dynamic. You can have a structure of structures that has an array of structures, and that structure has a bunch of structures, and some of those have arrays. It's turtles all the way down, my friend. All right, now let's look quickly at some of the dynamic reflection you can do on these things. So let's say I only want to write to a value if it exists in the structure. I don't want to try to write to it if it doesn't exist. That's going to cause a big problem. So how do I do that? Well, we can do auto ref is equal to, and then we'll index into our buffer. So I'll talk a little bit more about this in part 2, but what this is doing is it's not returning a dumb reference to, you know, an XM float 2. It's actually returning a smart proxy object. And what we can do is we can check that proxy object to see if it's actually a valid key in the data structure. We can go ref.exists. So we do if ref.exists, then we can write to that part of the buffer. So here we key into the structure, make sure it exists, and it does exist, so we write to the structure. What happens if we try a key that doesn't exist? It's going to try to key into the structure, but since this key doesn't exist, the reference, when we call exists on it, it's going to return false, because it is what I call an empty reference. So this allows you to speculatively try to access members of a structure, and if they don't exist, no harm, no foul. I also have this helper here, set if exists, and that will set if it exists, or if not, it'll do nothing. It's also possible to get a pointer to some bytes in the buffer. So that looks like this, and then we could use that pointer to directly set those bytes. So we get the pointer. If we look at P, yeah, it says it's pointing to something that has a value of 69. And if we set that, now it's 69.696969. And if we look into the buffer, at the very end of the bytes here, yeah, we got our 4 bytes from that setting. Finally, the buffer supports const correctness. So if I do a const auto reference, we'll call it cref, and we'll initialize that as a reference to the buffer. You can see here, if I try to get a non-const pointer, it won't let me. If I try to do an assignment, it's not going to let me. But it will still let me read from the data structure, no problem. All right, that's pretty much all the important syntax for this bad boy. Let's take a look at some places where it's actually used to wrap up section 1 of this video. So if we look at mesh.cpp, we can see now for the constant buffers, I mean, obviously I'm going to be using my new layout system. So you create a raw layout, you add all the members that are required, create the buffer, initialize those members to whatever values you want to have them in, and then you create your bindable. It's that simple. And we had to create a new bindable, right? Because now it's not, the old one was templated, statically templated on a structure. This new one is going to take in the dynamic constant buffer structure type. So if we look at constant buffers EX, right now, what I'm doing is I've only got implementation for dynamic constant buffer for pixel constant buffers. Because Vertex, I haven't had much need for it up until now. Probably get to it eventually, but not right now. And there's two main versions. There is a caching version, and that stores the buffer right in the structure on the CPU side. It keeps a copy of the buffer contents on the CPU side. The non-caching version does not keep a copy on the CPU side. So when you update, it loads those values over to the GPU, but it doesn't maintain a shadow copy on the CPU side. That's the main difference between these two. And they work basically the way you would expect. This is the main constructor that you would use, and you pass it graphics, you pass it the buffer, you pass it what slot that this constant buffer should bind to, and it'll create that stuff for you. There's also an alternative version that takes a layout instead of a buffer. So you can tell it to create a new empty buffer. You're not giving it any data, and just tell it what the layout of that buffer should be. But normally you're going to use this one right here. You're going to create your buffer, and then you're going to create your caching pixel constant buffer EX from your dynamic constant buffer. And that's it. That's part one out of the way. Hopefully when I edit this down, it won't be too long. And that should be the minimal that you guys need to get an idea of how this code works. So when you see it in future videos on other topics, it's not going to throw a monkey wrench into your understanding. You'll be able to follow no problem. I anticipate that actually having this system in here is going to make the other videos more streamlined. It's going to make the process a lot better for me because it's going to be easier to develop stuff with constant buffers. There's more error checking. I don't have to figure out the alignments and stuff. So if you don't like anything C++, you're not interested in software engineering aspect, architecture aspect of this, you just wanted these videos for the API and the graphic stuff, you can peace out. See you guys later. No harm, no foul. But for those of you who are interested, we're going to move on to the motivation for this design and give a little bit of overview of what the design looks like. All right, let's talk about the motivation behind this system and what it gains us. So with this, we have dynamic composition of the data structures, right? We can configure them dynamically at runtime in response to information that we may only be able to get at runtime. And that's pretty powerful. We take a look at the system before I implemented all the dynamic constant buffer stuff. Look at mesh.cpp. This big ass chain of if-elses, the main reason why this exists is because we need a different static constant buffer structure for every different configuration of resources that a mesh has, right? Now, if we could compose this dynamically at runtime, if we could just, for example, if we detect that this mesh has a diffuse map, if we could just add in the things that a diffuse map needs and build them all up, we wouldn't need this big long if chain where we duplicate a bunch of code for every possible combination of resource types. And sometime after the dynamic const stuff, I actually do that. So let's look at my current code. What do I have right now? So this is the future code, a little bit of a sneak peek at what it's going to look like in the future. I have a file here, material.cpp, and for the Phong technique, to build up all the stuff in the constant buffer and in the vertex layouts, you just check for each thing. We're going to check, do we have a diffuse texture? If so, we're going to append texture 2D to our vertex layout. Now, if we don't have a diffuse texture, we're going to add a constant color to our constant buffer. And the same idea for specular, for normal maps, and here's just some common stuff for all of them. So this handles all of the cases, and it's maybe, it's less than 100 lines of code here. Now again, compare this to the old system. It starts from line 380, and it goes, and it goes, and it goes all the way down to 730. 350 lines of code versus about 100 lines of code. Which would you prefer? So that's one benefit, the ability to dynamically compose our structure at runtime. The other thing is that we can dynamically query the structure. We can have our code dynamically read the layout of our constant buffer. And that's called reflection. Take a look at mesh.h. Remember the whole thing we had here where we had the ability to control different meshes? But since meshes are polymorphic, different meshes are going to have different constant buffers, but they're all statically templated, and it was a nightmare to figure out which is which. We're only supporting two different kinds of constant buffers here, two different kinds of meshes. And even with this, we've got this const expression, if, and then we've got a dynamic if inside of that. And we're going to have to do that for every single one that we want to support. And then mesh.cpp here, we've basically got to call control me daddy with every single different kind of static buffer struct that we want to support. When we call with the first one, if it fails, then we try calling with the second one. And if that fails, we'd have to do the third one, the fourth one, the fifth one. It's just retarded. With the new dynamic constant buffer system, we can just query, does it have a normal map? If so, provide a checkbox for that normal map enabled control. Does it have a member called specular map enabled? Put a checkbox for that. And then any kind of constant buffer, it doesn't matter if you have 3 types of constant buffers or 300,000 types of constant buffers. If it has that member, you can support it with the appropriate control. You can take the appropriate action. All dynamic. It's beautiful. It's poetry in motion, my friends. And that's not all you get, because in the future, we're going to do something called shader reflection, where we can reflect on our shaders. We can read the contents of our shaders, what kind of constant buffers they have, what are the members of the constant buffers, what are the parameters the shaders take. We can read all that information at runtime, and then we can use that information to build our dynamic constant buffer on the CPU side, so it will always match, and it will always react to changes to the shader code. And we can realize a single source of truth, and that's an amazing thing to have. Even before we do that, we could also just, if we're defining a constant buffer on the CPU side, we can use reflection to just do a check to make sure it matches what it's trying to load on the HLSL side. And there's more, because as I've shown you, our system here, it automatically calculates padding for us. And that can be a huge source of human error that can waste hours of debugging time over the course of a project. So this system does that annoying boilerplate layout for you automatically and without fail. Is that enough motivation? I think it is. Moving on, let's take a look at the actual design of the system. Now, if you watch my video on the dynamic vertex buffer, and I hope you have, a lot of this is probably going to seem familiar to you. It is the same, but different. So we can conceptualize it like this. A buffer has 2 parts to it. I've already shown you this in the first section of this video, but you've got the layout and you've got the actual bytes. The bytes is just the raw bytes of the data. These bytes can be directly copied over to the GPU and you're good to go. Now the layout is what tells you what makes that connection when you try to key into a structure or index into an array. You're going to be navigating the layout in order to arrive at some offset into these bytes. So it provides the map of the landscape of this just dumb buffer of bytes. And at its heart, it's a tree structure, right? Because structs can have members, just plain data members like bool or float4, but they can also have other structs, and then those structs can have structs. So conceptually, it's a tree, and in practicality, in the actual implementation, it's also a tree. Every element of the layout here stores the offset into its position in the bytes here. You use the keys to navigate this tree to arrive at a leaf node. That gets you an offset, and you can use that to read and write to and from this buffer of bytes. Seems easy, right? Well, maybe not that simple. There's actually quite a few objects that go into building this system. Dynamic constant buffer isn't just 1 or 2 classes. It's a whole ecosystem of classes that work in concert to provide that syntax and to provide all that type safety and correctness checking. You should be familiar with 2 in here right away, because you've seen them in section 1. That's buffer and raw layout. And these are the 2 forward-facing classes that you're going to be interacting with the most when you use this system. All this other stuff is kind of just behind the scenes. Now, before we talk about that behind the scenes stuff, let's just quickly go over the notation that I'm using here so that the diagram makes a little more sense. You can see that there are different colored lines. The blue lines mean referencing, by reference or pointer, or they mean ownership, usually by smart pointer. So for example, a layout object is just a shell that contains the tree of layout elements. So a layout is composed of one or more layout elements in a tree structure. Likewise, a buffer also has layout elements because it needs a layout in order to describe the configuration of the bytes in its raw buffer. You're probably familiar with the white lines. This is just inheritance, right? So for example, for a layout, this is the base type, but there's a raw layout. That's the one that you use that you can, add members to, build it up, configure it. And then there's a cooked layout. A cooked layout cannot be changed. The third kind of line here with the circles, I don't know what to call this one. Maybe I call this one interface. Maybe I call it pooping because, and you'll be familiar with this if you've watched my video on the dynamic vertex buffer. But when you want to access members of the data of a buffer, you index into it or you key into it. And what that's going to return is that's going to return a proxy type that is a proxy to the bytes of the buffer. And that proxy type will implement interfaces for the assignment operator. So if you try to assign to it with a float, it will try to write floats into the correct bytes in the buffer. So these yellow ones mean, when you index into it or when you do a conversion or assignment, it's going to try possibly to poop something out that will handle that. So these yellow lines, they mean that, when you try to index into something, it's going to poop out a proxy type that will represent that thing that you index to. Or the yellow lines can also mean that, if you try to assign to this proxy type, there's an operator for that is going to take that assignment and use it to modify the bytes in this buffer. So that's the basic notation. Let's get on with the system. So what do we have here? Well, let's begin at the beginning. You start off, you create a raw layout, which is a kind of layout. It will have a root layout element that's a struct. When you index into the layout, it's going to poop out a reference to your root struct. And then you can do things like call add on that struct. And in doing this, you can build up a tree of layout elements. Now, every layout element, it stores the type, whether it's a float or whether it's a matrix, a bool, those are leaf types, or whether it's a struct or an array. Now, for the leaf types, all you need to store is the type, which is an enum, and the offset. That's all you need. But for struct and array, you've also got to store extra types, right? Because a struct, its members are also layout elements. So a struct is going to have a vector of layout elements, and you can have, so if you have a layout element that's a struct, it's going to have a vector of other layout elements, and maybe this one is a struct, so it's also going to have a vector of other layout elements. You get the idea. Now, an array layout element, it doesn't have extra data as a vector of layout elements, because an array only has a single type, right? You can have an array of float, or you can have an array of matrices, one type. So it's going to store just a single layout element. So because you are storing extra layout elements for the special layout types of struct and array, we have extra data that is optionally owned by the layout element, depending on what type it is. You'll see this in the code later on. But you're going to have a tree of these. That's this thing right here. That's going to be owned by a raw layout. Then when you want to create a buffer, you're going to pass the raw layout to the buffer. The buffer is going to cook the layout. That's important, by the way, because when you build up this structure, the offsets aren't fixed because it's still changeable. You could still add members in between and stuff like that. So what happens is you build up this raw layout. It determines the tree structure, but the offsets aren't determined until you cook the raw layout. So when you pass it to the buffer, the raw layout gets cooked. You have a finalized layout. From that finalized layout, you know how many bytes you need. So then the buffer can create its array of bytes, and it has its layout, and it's all good to go. Now, once you have a buffer, you're going to want to start accessing the data in that buffer. You declared a layout. Maybe it was a simple struct with 3 floats. You want to access those floats. So you access them by their name. You use the index operator, right? You key into the buffer. The buffer navigates its layout elements finds the matching one, and what it does is it returns a reference, element reference. And what this element reference is, I call this a proxy type. It maintains, this diagram says that the element reference maintains a reference to the buffer. That's not exactly true. It actually maintains a pointer directly to the byte array of the buffer. So it has a pointer to the raw data, and it also has a reference to the layout. Specifically, let's say we've got a tree like this. If I index into the buffer with A, element ref is going to point to this layout element, and it's going to point to the byte buffer. And then if I try to assign a value, it's going to look at element A, it's going to get the offset. It's also going to check to see if the types match, if this is actually, if I'm trying to assign a float, it's going to check to make sure that this is a float, and if it is, gets the offset and writes into the proper place in these bytes. So that's a simple scenario of, this line of code here. So what about this line of code here? Now we're indexing or keying into a path, B and then D. So what happens? Well, first, we index into the buffer B. It looks through, or basically asks this root struct here, do you got a B? And it says, yeah. So it gets that B. It returns you an element ref that points to this B, and that points to the data. Then you index into this B with the key D. So again, now you're calling this one, element ref, checks its B, it says, do you got a D? Oh yeah. So it poops out another element ref, this element ref pointing to D. Buff poops out an element ref, which poops out another element ref, and this element ref points to D. Now we want to assign, does a type check that says, is D a float? Sure. So using the offset of D, which let's say is here, it writes the correct bytes into the raw byte buffer. And that's how it works in a nutshell. Now, element ref acts as a reference, logical reference to some element in this buffer here. What if I wanted a pointer to these bytes in the buffer? Well, you might say, I'll just do, address of buff at, some key. Well, what is that going to do? This returns an element ref. It poops out an element ref. We're going to get the address of this proxy object, which is not going to be the address of these bytes in here. So that's no good. So if we want to be able to get pointers to these bytes, we have to implement our own address of operator for element ref. So that's what we do. When we do address of on an element ref, it is going to poop out a proxy type, which is similar to element ref, except that instead of converting to a reference to T, it converts to a pointer to T. And then you can use that, you can store that pointer and use that to directly manipulate the bytes in this buffer. So this is just a little bit of a helper to make life easier, to make the syntax sexier, not strictly necessary. And down here, we have constant element ref, and it has its own pointer type. And these guys, similar to element ref, they allow, indexing or keying into the data structure. They allow conversion, but they don't allow assignment. And the conversion is only to a const reference. So if you have a const buffer and you index into it, it is going to poop out a const element ref, which will not allow you to modify anything in these bytes, only to read them. So this enables const correctness for when you want it. And that's it. That's basically the overview of the system design here. It does a lot of things, got a lot of neat features. There are many, many more features that I had gone through my mind that I had considered that I might add later on. I got a big wish list, but you can't just keep building things and keep adding features to something like this. You'll never get your main project done. So I built what I needed, and I left the rest as maybe one day if I find a real need for it. There are many things that I know could be added to this and that would be neat. Believe me, I'm aware of it. One of the things that I'm very likely to add is the ability to iterate over the tree of layout elements as part of reflection. Because right now, the only reflection you can do is you can check to see whether a particular key exists. Oh, that reminds me, one more thing. So let's say you got a layout tree, 2 elements, A and B. We know if we index in with A, it's going to poop out an element ref that maintains a reference to this layout element. But what happens if we try to index in with an element key that doesn't exist, with a C? Well, what this does actually is there is a special kind of layout element. The type is empty. So if you try to index into a struct and that key doesn't exist, it doesn't fail, it doesn't throw an exception, it doesn't bug out. All it does is it poops out an element ref, but this one, its pointer points to a single empty layout element. This just exists statically. It's a global, basically. So when you have an empty one, now if you try to assign to it, if you try to convert, that will throw an error. But you can call the function empty, and it will return true for an empty element ref that points to an empty layout element. Or I should say to the empty layout element. And this is what is enabling the basic runtime reflection that we have right now. Like I said, in the future, I will have a way of iterating over the entire tree and, asking every layout element its name or whatever, name and type. But for right now, we can just query by checking empty or not. But yeah, that's the basics of the system, the overview of the system architecture and design. And I believe this will be part 2 taken care of. All right, now the fun part. Let's actually dive into the implementation code. Dun, dun, dun. It's very scary, but don't worry, I'll be here. We'll get through this together. Let's hold hands. So, dynamic constant.h, dynamic constant.cpp. These are the implementation files. Everything for dynamic constant is inside the namespace DCB, except for this macro, which obviously doesn't work in namespaces, but this macro gets undefined at the end of this H file, so it doesn't pollute anything else anyways. So quick overview, we have an XMacro list of all the types we want to support. I'll talk about that in a little bit. And then here we have a lookup map for attributes about every one of these types. This is for compile time lookup via templates, and you've seen me use this in the dynamic vertex buffer system, but I'll talk again very quickly about it. Reverse lookup. Here are the actual classes. That's what you saw in the diagram. We got the layout element. We have layout, which is the base, and then raw layout and cooked layout inherit from it. Then we have const element ref, and then we have the buffer. As you can see, I have filled this source file, the H file, with a buttload of comments, which I don't normally do, but I figured for people who are really interested in this, if they actually want to read the code, I'll add some words in here. A little bit of side commentary by Chili might help you read through it a little easier. I don't know. Well, let's take it from the top. So this is an XMacro list. What it allows us to do is it allows us to define the list of these different leaf element types, the types of layout elements that we want to support, the actual raw data types, excluding struct and array. So we can define those types, their names, in one place, and then this can be replicated in a bunch of different places all throughout our code. So normally, if we had a bunch of switches that were switching on these names, and we do, if we added one, we'd have to also add to every one of those switches. But with an XMacro, it will automatically, all that other code will react when we add a new name to this list or when we remove a name from this list. So how does it do that? Well, we can see here, normally with a macro, you would define, the signature of the macro and then what it expands to. But with this one, it's a little different. We are actually invoking, we're defining a list of invocations of a macro called X. But there is no X macro. So how does this work? Well, what happens is when we type leaf element types, it is going to invoke this X macro on every one of our types. And what we can do is before we invoke this macro, we define what we want X to be. And that will allow us to replicate these names with some transformation. So for example, we have an enumeration. This is all the different types of the layout element. Just a simple enum. You can see we got struct, array, and empty in here. But for the actual data types, we're using XMacro to expand this. And all we're doing is we're getting these names plus a comma at the end, because that's what a enum looks like. So we just expand all these names, add a comma to the end. That's what this XMacro does. We define the transformation for X that will be applied to each one of these. Then we invoke the XMacro, and then we remove the transformation because we don't need it anymore. So that's how it works. And now one thing that you can't use the XMacro for is for our attribute map, right? So we've got a template here. You've seen me use this again in dynamic vertex, but we're templating on this enum, and then we do template specialization. So when the template parameter is float, then we have all these const exprs that we can read into in our code. And you can see here I'm just defining the type, the sys type. So when the layout type is float on our system, that's just a float. But when it's float2 on our system, that is a DirectX XM float2. Also the size of that type on the GPU, which is, we need to know that for alignment purposes and for packing purposes. Usually it's just the same size as on the CPU, except for with a bool, on the CPU side, bool is 1 byte, but on the GPU side it's 4 bytes. So we can't use size of sys type. We've got to manually specify it as 4. Code here is for, this is for the signature. We'll talk about that in a little bit. And then valid, true. Well, if we pass in these specializations, they're all valid. But if we were to try to specialize this map on, let's say, string, it would not resolve to one of these specializations. It would resolve to the generic one, which has set valid equal to false. And there we can detect whether a specific type is valid in our system. It's not really likely that one wouldn't be valid. But for example, if we tried to map struct, which is a member of this enumeration, to an attribute map, it wouldn't work, right? Because the struct isn't an actual data type, it's an aggregate. So that's what this is for. It allows us to detect bad situations like that. And actually, I use it here. This is a neat thing, because like I said, with the X macros, this list is very reactive. We add a member in here, and everything automatically changes, except for the attribute map. You have to add it manually. So when you add a new type, you have to add it here and here. But what if you forget to add it here? That's a problem, right? So what this X macro does is it expands to a static assertion for everything, for every one of these guys in this list. It checks to make sure that there also exists one in here. So it does the map of that type, and it checks to make sure it's valid. If not, it prints out a nice message. This message will come out in compile time and will help us, and we'll say, oh, duh, we added one in here. We forgot to add its attributes. Let's do that now. Very nice. Similarly, we use X macros here to define a reverse map. So every one of these enumeration values, these ones here, they each have a corresponding sys type, like float or XM float2. Now with these maps, we can go from the enumeration to the sys type. But what if we have the sys type and we want to know which enumeration it's for? Well, we define a reverse mapping using our X macro, and it will expand out this template specialization for every one of the types. So for, float, float2, float3. And then we use a map from that to get the system type. So now we have a struct, a reverse map that's templated on system type, and we can use that to get the enumeration type. And again, we have the valid check. This one defaults to valid false. So we can check to see if a specific system type is mappable in our system at compile time. So there you have it. There you can already see the power of the X template system. It means you don't have to change, if you want to add one thing to the system, you don't have to change 50 places in code. You have to change exactly 2 places. And if you forget one of those places, this is going to tell you. So it's very clean. Very safe. All right, now let's jump into the layout element. This is the heart of the whole system. This is the cornerstone, the building blocks of the layout tree, right? All right. So right away, we've got this struct here. It's got a virtual destructor, so we know we got some polymorphism. It's called extra data base. And this is the base class that the two extra data classes will inherit, the extra data class for struct and array. We'll get into that in a little bit, but here is where the base is declared at. We got some friend declarations. You got lots of friend declarations because this is a whole ecosystem of components that work together and that need to, I make it so that the objects within the ecosystem can access their own members for convenience, for building the ecosystem. But I still want the outside world to not be able to access a lot of that functionality because they only need the functionality of, declaring the layout structure and then accessing the buffer. All that other stuff, they should not really be allowed to access. That's just extra noise that is going to add to the cognitive load of anyone who's trying to use the library. So I make many things private, but then I make friends able to access those things within this ecosystem. All right, functions. Get signature. So a layout tree, which just describes the layout of a structure, it has a uniquely identifying signature. We can use that signature to, for example, store a codex of layouts and to share layouts, which is actually what I do. So get signature is a recursive function that recursively builds a signature. Actually, let me just show you guys that right now. Here's the code from the testing. So you can see this code here builds a fairly complicated structure. It then creates a buffer from that. And then we can get the root layout element of our buffer and then get the signature of that, which is the signature of the entire layout, right? So let's do that. Step over this and let's look at sig. We can expand it here. So this is the signature of that entire structure. And this uniquely identifies this. And theoretically, we could also use this as a descriptor to reconstruct a dynamic structure. I haven't implemented that yet, but it's something that might be possible in the future. We could serialize the layout, and then we could read the layout from a file. It's something that is highly possible, but I will implement only when I have a good use case for it. Again, Yagni. So that's what getSignature does. Exists. You've seen it. It checks if the element is real. So well, let's first take a look at the data. Getting ahead of ourselves. Every layout element has three members. It has the offset into the byte array. And that's optional, by the way, because offset is only valid after you have finalized the data structure. So we got the offset. We have the type, which defaults to empty, by the way. And then we have a unique pointer to extra data, which may be empty for most types, but for a struct or an array, it is going to point to some dynamic data. All right, and all exist does is it checks to see, is this equal to empty? If it's not empty, then it returns true. Calculate indexing offset is a very tricky one. Let's come back to that a little bit later. Has to do with arrays, by the way. But here's a very important one that allows us to key into a struct, pass it a string, and navigate into one of the members of that struct as a non-const and a const version. So let's take a look at the implementation of this. Well, the first thing you need to know is the extra data. So I got a struct here that holds the extra data just for reasons not that important. But then we have struct and array. So extra data struct, extra data array, and they inherit from extra data base. And the struct one, the extra data for a struct, is it needs a vector of layout elements, but it also needs to store the key names for each of these elements. So it's a vector of a pair, pairs of string and layout element. I could have also used map or unordered map, but I don't think for the number of elements that typically our structures are going to have, I don't think map or an unordered map would be a good choice. Probably more overhead than it's worth. So we're going to stick with just a simple vector for right now anyways. And that's for struct. And for an array, it doesn't need a vector of layout elements. It just needs a single layout element that describes its type. And that'll be optional because when you create an array, remember, you first create it and then you call set to set its data. So initially data is not going to be initialized. So that's why I make this optional. And then the size is just the number of elements in the array. So these are the optional data boys that those aggregate layout element types will also own. Now, what was I doing here? I'm getting sidetracked. I believe we were looking into, yes, the keying in operator, index operator, takes a string. First we do a simple test to see, is this actually a struct? This is only a debug time test, by the way. In release, it's not going to do this check for you. If so, then we static cast our extra data because we don't know what it is. Remember, it's polymorphic pointer to base type. We don't know what it is. So we're going to static cast that to extra data struct. And we want to iterate through all the layout elements. And then we're going to check to see if the key of every layout element is equal to the key that was passed in. And if so, we're going to return a reference to the layout element, which is the second member of that pair. If we loop through all the layout elements and we still haven't found it, we return GetEmptyLayoutElement, which, let me see if I can find it. Oh, interesting. This one escaped me. I moved all the definitions over to the CPP file. I missed one here. But yeah, here it is. GetEmptyLayoutElement. It creates a static singleton layout element. And that's default constructed. So that means that its type is going to be empty. And then we return that. But yeah, that's how you index into a struct. And in the const version, it just does a const cast. But it calls into this one. This is the reference implementation. There you have it. That's probably one of the more complicated parts of this. Most of the functions in this class are very simple when taken one by one. So yeah, that is the indexing into a struct. This just gets you the type of an array. Not that complicated. GetOffsetBegin just returns this offset. GetOffsetEnd is tricky. It depends on the type that we have. So what we end up with here, GetOffsetEnd is a switch on the type enumeration value. And again, we got our XMacro. So if it's just one of the simple leaf types, the offset end is going to be the offset to the beginning plus the size on the GPU. Pretty simple, right? But if it's a struct, what we do is we get the offset of the end of the last element in the struct, and then we add the padding, advance it to the next 16-byte boundary. So you see the logic is a little different for struct, and it's a little different for array, because they've got to, they have to add padding after the last element, stuff like that. But that's the basic idea. And GetSizeInBytes, this one is just offset end minus offset begin. So these guys here, because offset is only set after you finalized, do not call these guys if you haven't finalized a layout. They're not going to give you good data. They're going to throw an exception in debug mode. In release mode, they're just going to give you garbage. Then we got a function to add a new element to a struct. It's not that complicated. Make sure that the thing we're trying to add to is actually a struct. Make sure that the name is a valid name. Then we are going to loop through all the elements in the name in the struct. Make sure that we haven't duplicated the name, and if not, then we're just going to in place a new layout or a new pair, which has the name and has a layout element constructed with that type. So I mean, there's no real big surprises here. This just sets the type for an array. We've got these templates here. And this is a little complicated, but basically the system went through some evolutions, and in previous iteration, it used this template here because it wasn't an enumeration, it was actually separate types. And so it needed to be templated. And then I rewrote it all after the fact. So all the code, existing code, uses this interface. I couldn't just get rid of it, even though it's not necessary. I kept the template version, but it just calls the non-template version. And then here's the resolve. This is used whenever we're trying to read or write from bytes in the raw byte buffer. And all it does is it adds this assert in here to make sure that the type that we're trying to resolve to is equal to the system type corresponding to the current element. So if we're trying to resolve to a float, it makes sure that the thing that we have is actually, a float. And if so, it just returns the offset. If not, it's going to, throw an exception telling us our programming is bad and dumb and we should redo it. Also, if you try to resolve for something that isn't a base data type like a struct or an array, doesn't make any sense. That's also going to throw an exception. Then we got constructors. They just work basically the way you would expect them to work. Finalize function. You call this on the root of the layout tree, and it will recursively finalize all the nodes in the layout tree, calculate all their offsets, and everything's good. So what it does is it works through the tree, and you pass it in. As it's working through the tree, it builds up just the flat array, right? So your offset is going to be steadily increasing. So your finalize keeps track of current offset, and when it calls offset, or when it calls finalize on a child, it passes in the current offset. The child returns the new offset after itself, and that's how things are built up. So I mean, if we look at the implementation of finalize, if I can find it here, yeah, very simple. For a basic data type, we set the offset equal to the offset that we pass in, but according to HLSL rules, if we've got a float 3, for example, and it's crossing a 16-byte boundary, we have to make that float 3 start at the new 16-byte boundary. So we got to push it up, add some padding before it. So this adds padding before if necessary, sets up the offset for the current thing, and we got to return the offset at the end of the current element. So that's just offset plus HLSL size of the current element. So again, XMacro does that for all the different types, making good use of our map. But obviously, for non-basic types like struct and array, there's going to be more work, right? Struct is going to be recursive, and array is going to be a little bit recursive, right? So I factor those out into their own functions to make things a little cleaner in here. Here's the implementation for finalize for struct. What do we got here? Make sure that you actually have at least one element in the struct. You advance to the next boundary. Structs always have to start at a 16-byte boundary. And here's where we're keeping track of offsets. So we call finalize on each of the members of this struct. We get the next offset. We pass that offset into the next element, and that is how the byte buffer is filled, basically. And of course, some of these members here, some of these elements, could also be structs, in which case recursion happens. Similar for finalize for array, except there is no loop, because an array only has a single type. What else do we got here? Advance the boundary, just pushes it up to the next boundary if it's not already on a 16-byte boundary. Check to see if a block of memory crosses a boundary or not. Advance if a block crosses a boundary. Validate the symbol name. What are the rules for the symbol names? I don't remember what I chose. So front can't be first symbol can't be a digit, can't be empty, and it all has to be either underscore or alphanumeric. And there you have it. That is your overview of the layout element, which forms the tree. That is the map. That is the heart of our dynamic constant buffer system. The other stuff is not that hard. A layout is just a basic shell that is used to transport this tree of layout elements. So it has a pointer to the root of the tree, as this, and some functions to get the signature of the layout and the size and bytes of the layout. That's the baseline, which is inherited by raw layout. Allows you to index into that. That's how you build up your layout as you're defining it, and also add, very important boy, because you're able to add obviously elements directly to the root. So you need this interface function here. Once you've gone one level deep, you'll have access to all the functions that are in layout. Where is it? Layout element, right? Because once you index, you get a reference to layout element, not another raw layout reference. That wouldn't make any sense. Yeah, and some other functions here. Clear the thing to deliver the layout, the whole tree, for transplanting somewhere else. And then you've got a cooked layout. which is similar, except it allows you to index in, but does not allow you to add. And when you index in, you get a const reference, so you won't be able to add after indexing either. It prevents you from mutating the layout, which would be a bad thing after it's been cooked. Would not be a good idea to mutate that. But yeah, not a big deal. Here we've got the proxy types, the proxy boys. Here's where all the that syntax magic happens. That allows us to, assign directly to our indexed things, and it just looks like something that was built right into the language. This is where the sexy happens. So as before, it allows you to do the exist check. Well, let's take a look at what does an element ref. Let's take a look at just a normal element ref actually. So what kind of data does it have? Well, it has the offset. This is, I should have renamed this. The name isn't very good. This offset has to do with array indexing, which is the most complicated part of this system, I believe. So I'll talk about it last. The two main things that these references store is they store pointer to the layout element that corresponds to the reference, and a pointer to the dumb byte array, the beginning of the dumb byte array. And so, you can index, or you can key into them or index into them, and that will return another element ref. And that corresponds to this operation right here, right? Index into element ref, you get another element ref, you traverse the tree of elements. You can check to see if it exists. That just calls exist on the layout element. You can set if exists, which is just a wrapper around exists plus assignment. The main boys here are the conversion and the assignment. These are templated, so they will allow you to try to convert or try to assign any type. However, when you actually do that and the compiler tries to instantiate this template, say that's, for example, you try to assign a float, first it's going to do a static assert. It's going to check to see whether a float is even possible. Is it in the system? If not, you're going to get a compiler error, and I demonstrated that in section 1. If it is possible, if it is within the type system, that sys type that you're trying to convert to, then it will perform the resolve on that type, and it will do the dynamic type check in debug mode to make sure the types match. And it's going to calculate, basically this is going to give you the offset into the raw byte buffer, and we add that to the beginning of the byte buffer to get a pointer to the bytes of this element, and then we're going to reinterpret those from car into the actual system type. Forget about this offset for right now. I'll talk about that at the end. It has to do with array indexing. But yeah, that's for conversion, and a similar thing happens for assignment. All assignment does is it calls into conversion. So it static casts to a reference to that type and then assigns. So now that I think about it, this static assert here isn't strictly necessary. It's already covered here, but might as well give it a good go here as well. Catch it at the first point of problem. But yeah, this is the stuff that enables the cool syntax. If you want to get a pointer to those bytes, we overload the address of operator. It returns a pointer, which is defined here. And pointer actually maintains a pointer to the element ref that pooped it out. Now this is a little bit dangerous because this can become invalidated if you capture this pointer object by value and then the element that spawned it goes out of scope. This will be a dangling pointer. So this is a disaster waiting to happen. I'm aware of it. I was aware of it from the beginning, and I might fix it in the future. I'm entertaining a number of ideas. Some of them will require a little bit of code duplication, but I'm willing to do it. Some of them, I don't know. We'll see. But anyways, poop out a pointer, and the pointer supports a conversion to T star instead of the conversion here of T ampersand. And that allows you to do your pointer stuff. And there you go. There's the thing. Const element ref is the same idea, except it doesn't support the assignment, and it converts to const t-and, and its pointer class converts to const t star. And by the way, non-const element ref has a implicit conversion ability to const element ref. So you can get a const element ref from a non-const one if you want. But there you have it. Those are the boys, the proxy boys that do the stuff. And finally, the buffer. And it's not that complicated. It just houses a layout root, and it has the vector of car, which is the raw bytes that actually store the data. And again, you can index into it with a key, 2 versions, non-const version. Const version will give you a const element ref. That's how you enforce the constness. Get the data, get a const car pointer to the data, very important for when we actually want to use this. For example, copy the buffer over to the GPU. Get the size, get the root layout element. Later on, this will be useful for reflection stuff. We'll be able to iterate over the entire structure and read out its dynamic name and type. You can copy one buffer to another. You can get a shared pointer to the layout element. You notice that it's owning layout element by shared pointer. And this is so that multiple buffers can share the same layout. Layouts are static. Once you've created them, they are immutable, right? They're cooked. And so any number can be shared, and that's really good for memory caching. Yeah, there you have it. You can create a buffer in a number of ways. The most common way is by passing it a raw layout. You move a raw layout in, it will cook the layout and eat the layout. Delicious. But you could also pass it a cooked layout, or you could pass it a buffer and it'll copy that buffer. And I believe, yeah, if you copy the buffer, it'll copy the buffer's layout, and it will also copy the bytes of the buffer. So that's nice and convenient. I didn't implement assignment, but I could. Maybe I will someday. Who knows? For right now, this is doing it for me. This is doing it for me good. All right, now it's time to face the final boss. And that is indexing into an array. So let's see if I can explain this to you without making your brain explode. So let's say we got a structure. Here's the bytes. I won't give each byte its own line. I'll give each float its own line. So let's say it's got 2 floats. We'll call them F1, F2. Then it has an array of structures. And we'll just make it 2 wide. And those structures each have 2 float 2s. So this is padding. And here we have, this is an array. Its name is going to be A1. And it is an array of structure type. That structure has 2 members. And those members are going to be named Poo, P. Because my brain is, I've been recording for quite a while. My brain is starting to cook in my head. So, looks like this. Now, normally when you index into a buffer, let's say you're going to index and you want to get F2. What's going to do is it's going to navigate the structure. Well, let's draw the structure, I guess. So you got the base. And then you have 3 members. F1, F2, A1, and A1 has a type. Well, this is the type T of A1, and it's a structure, and it has poo and P. So this is what the tree looks like. Struct here, and array here. All right. So when you index normally into an array, and you want to, assign to it some value, it is going to call resolve, and that is going to get the offset stored in here, and that offset, it can be directly used to write into the byte buffer. It's just a direct offset number of bytes into the byte buffer. But with an array, you can't do that. If you do buff, A1, get element 1, which is this one here, and then get the P of that element. Let's think about it for a second. This is the conundrum that I had to face when I was implementing this. So every element here stores its offset. So the offset of the root is the beginning, which is also the offset of F1. The first element of the struct has the same offset as the offset of the struct itself. Second element, its offset is here. The offset of this array is here. The offset of this struct is also here, the beginning of the array. The offset of poo points here. The offset of p points here. So if we just use the offset of p directly, it's always going to access this one. But we want to take into account this index number. So we have to add an extra array indexing offset. So we get the offset from p here, and then we add to it the array indexing offset, which is going to be size of the array, the structure t times the actual index number, which is going to be 1. And that will add from here and get us to here, which is the correct answer. Now the trick here is that you can have arrays that contain structures that contain arrays, and those offsets will all add to each other. They all accumulate, and that is why this exists. So when you poop out, let me just show you here. When you index into the buffer for the first time, you're going to poop out an element ref. Is going to have a pointer to the element root. Is going to have a pointer to the key. Is going to have a pointer to the element, the layout element that corresponds to the key. So it's going to index into the element root and get the layout element for that. It's going to have a pointer to the data bytes. And the offset is going to be 0 because there is no array indexing, right? Not yet. But whenever you index into an array, it is going to calculate that indexing offset by taking in the current array index offset and the index value and calculating the new indexing offset, and it's going to pass that in. So when you calculate indexing offset, it's interesting because it actually gets you the t, the the layout element, that is the t of that array, and it gets you the new array indexing offset. And these build on each other because you pass in the old array indexing offset and it adds to that. Whereas if you index as a struct, it just takes the old indexing offset and passes that through, never adds to it. So there it is. I don't know how many people will actually understand that explanation. It's kind of complicated, as I've mentioned. But that in a nutshell is why you have this size t in here. This is an extra offset that accumulates as you index into arrays deeper in the structure. And there you have it. There is the entire explanation of this system here. Now there's one final piece of the puzzle here, and that is, let me see here, layout codecs. So, like I mentioned before, layouts have signatures, and those signatures, layouts are, once they are cooked, they can be registered in this codex. And so if you have two different layouts, two different buffers that happen to share the same layout, they will actually physically share the same layout, and they will get benefits of, memory caching and all sorts of good stuff like that. So you can manually cook a layout. You can pass in a raw layout to layout codecs resolve, and it will return to you a cooked layout. So what it does is it gets the signature of the raw layout, checks to see if that signature already exists in the codecs. If so, it's just going to return the existing cooked one. If not, it's going to cook that layout, deliver root, will cook the raw layout, and then we'll poop it out, and that will be inserted into the map. And we can actually see in the constructor for buffer that takes a raw layout, it just calls layout codecs resolve on that raw layout. And there you have it. That is, wait, wrong thing here. Why did I cross this out already? I wasn't done. Now I'm done. Now the implementation overview is complete. I have described the salient parts of the system in a decent amount of detail. I don't know. You might still be scratching your head over the array thing. I don't blame you. It's hard, dude. It's hard. Come on. The final part here, history, evolution. Yeah, I don't want to talk about that. Nah, the video is too long already. There's no way I'm talking about this. However, if you're interested I mean, the Git history is there. You can see the old design, you can see the new design and how it's much better. Here you can see heroic rework of dynamic constant buffer system. And if you look at it, you can see it was basically a complete rewrite. However, a nice thing, because of encapsulation, I only had to pretty much rewrite these lines. I added a few tests here, but I didn't delete anything or change anything. But because of nice encapsulation, again, as we often see in this series, don't have to go and change a bunch of other code that depends on this. I just have to change the internal implementation, and all the code that depends still keeps working like it worked before. But yeah, you can look at this. You can see the code before this commit and after this commit, and you can see it's very different. If you're interested in, talking about this stuff, the history and evolution of this system, you can always, hit me up on the Discord or on the forum, and I'll be happy to talk shop with you. But I don't think we need to bloat this video with any more discussion like that. That's not going to be necessary. But anyways, there you have it. And I don't know. What do you guys think? I'm really happy with the system. It's working out great so far. Believe me, I'm aware it has its limitations. It has its things like, well, one big one is that the issue I showed you with pointer. And I will, correct them as I seem necessary. But for right now, it's working really good for my purposes. And I hope you guys get a kick out of this too, because it really shows you what you can do with C++. It's like you can remold almost the core language if you want to add like new features to it. That's the metaprogramming power. And you don't want to spend all your time in that design space. You'll never get anything really accomplished. But a judicious amount of time spent there can really benefit the entire experience and the success of a large enough project. And that's the kind of thing that C++ enables that not many other languages enable. So I hope you guys got a kick out of this. And if it's not your cup of tea, don't worry. Next video is going to be less of this kind of stuff, and it's going to be more flashy graphics kind of stuff. Specifically, we're going to be doing a little bit of a special effect using the stencil buffer. So I'll be teaching how to use the stencil buffer, and we'll use it to do a little special outlining effect. And that's going to lead into some other stuff about full screen processing. It's going to be a good time. But until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button, helps a lot. And now I'll see you soon with some more Hardware 3D.